Hello there. Today let's continue talking about polar coordinates. So now we are on level 2. And just like level 1, I'm going to be talking specifically about polar coordinates, but I'm going to try and keep my discussion general enough so that you could apply these ideas to any coordinate system. And I want to kind of clarify one of my goals with this series. I'm not talking about these coordinate videos because I love talking about coordinates. I just have this overwhelming passion for talking about coordinate systems. They are very important though, and it's very good to have a pretty solid foundational knowledge of coordinate systems. Not necessarily at the highest technical math level, but just a solid understanding of how coordinate systems actually work, before actually doing real physics problems, right? So one thing that I'm doing behind the scenes is I'm putting together a document in LaTeX that, summarizes not just in polar coordinates, but in Cartesian coordinates, cylindrical coordinates, and spherical coordinates as well. All of these ideas that I'm talking about here, in these foundational videos where I just discuss the ideas in polar coordinates, right? So that's going to be really, really helpful because it's going to allow me to make physics videos at a slightly higher level, but much faster, right? Because I'm not going to be concerned about, for example, explaining, what a volume element in spherical coordinates is. That's going to be in this document that I'll go ahead and attach to the description of the video, for example, right? So now I can just use that knowledge. And as long as we have a good idea of what those concepts mean, which is why I'm exploring them, in these videos, then we're good to go. I can pull out volume elements, or I can just say, this is the r hat unit vector, this is the time derivative of the r hat unit vector. I can just use that knowledge instead of feeling like I have to explain what that means in, physics videos as we do more complicated ideas. And of course, I think it'll be really helpful for people watching the videos to have that resource, at their fingertips as well. Alright, but with that, let's get started. So far in the level 1 video, we basically considered Euclidean space just as a geometric space in that video. But I addressed a very big problem by the end of that video, which is that ultimately we can't add points together, which really means that we can't do proper physics, just considering Euclidean space as a geometric space. Right? And so the solution, which we'll see very quickly, is we need to introduce Euclidean vectors. Okay, so what is a Euclidean vector? Right? Let me go ahead and put this guy down here. Right, so Euclidean vectors are arrows or directed segments, which means they have a magnitude and a direction, which point from, one point to another in Euclidean space, right? So if I have two arbitrary points here, P and Q, I can define a vector, call it PQ, which points from point P to point Q. And of course, then we can go ahead and just define the classic notions of vector addition, the classic tip-to-tail method, which I'm showing right here, and scalar multiplication, right, which just scales, some vector u up and down like I'm showing here by some scalar alpha. Right, so of course I'm calling these, these directed arrows vectors, right, specifically Euclidean vectors. But I do want to ask this question, right? There's a mathematically formal way of defining vectors in vector spaces, right? So do these Euclidean vectors actually form a vector space? You have to actually think about these axioms, with the definitions that I've defined here. Does this set of all arrows which connects two points, in space, does that actually satisfy, the axioms of a vector space? Let's go ahead and demonstrate one of the most important ones, closure, right? That if I have, two arbitrary vectors, right, A and B, and I add them together, that of course is going to output with our tip-to-tail method, some vector A plus B. And again, we can see that check A plus B is enclosed, in our space. It still satisfies the requirement that this is an arrow which connects two points together in Euclidean space. So check A plus B is part of our vector space. And then we can go through, define, a zero vector, null vectors, right? We can go through, we can define inverse vectors, right? such that, you get out a 0, right, etc., etc. And you can show that, all of these postulates are satisfied. So that's a really important step if we're claiming that these arrows, right, these Euclidean arrows are actually vectors. And we call this vector space, right, E2, right, where we're talking about, in this video specifically, a Euclidean plane of 2 dimensions, right? But what we're going to see is there's kind of a little twist on this vector space, okay? And we do need to address this big time. Right, so to make this little twist here, I want to do a little compare and contrast. So on the right here, I have the geometric representation of R2. R2 is a vector space that any person in linear algebra should be very, very familiar with, right? Right, so if you give me some vector v in R2, I immediately know this is the only way I can write down v. It has to start from this origin, and of course it's just going to point somewhere, and we're good to go. But in Euclidean space, there's an ambiguity now. Because if I give you the vector v and don't specify, a starting point of this vector, I'm going, oh, could this vector v start here, or maybe here, or here, right? These are all equivalent vectors. They just have different starting locations, right? And of course, a lot of the time, you're not going to be explicitly, really focusing on this point, right? But for example, you might say that the force vector acts on the center of mass of an object, right? So that's key. Now you specified that point. You weren't really thinking about it super explicitly, but just by saying, force vector acts on center of mass of my object, I've locked in a point. That's where the vector is acting, right? But there's actually a really big consequence of this, right? Which we can immediately appreciate, right? So in R2, we can define a basis for R2, right? Or a set of building block vectors, more or less, right? Where, for example, the classic basis, I could just go ahead and define basis vectors, like this, right? Here are the standard basis vectors for R2, in which case I could write out V as some linear combination of, these basis vectors where alpha and beta are scalars, right? But the point is, because we can only draw our vectors from one origin point, there's one basis that we can use. So that's really, really important because that's different from Euclidean space. For example, what's stopping me in Euclidean space from defining one basis here, right? Call this basis B1, but then at this point here, I introduce another basis B2. Maybe my basis here just looks like this. My basis vectors here look like this. And, maybe we'll go over here and I introduce a third basis B3, and I don't know, maybe it looks like this, whatever. And the answer is no, there's nothing stopping me from doing that. We can define a different basis at every point in, my Euclidean space. That's a big deal, right? And because Euclidean space is continuous, right, I can call these, I'll call them tangent bases, right? And I'm specifying that I have a tangent basis. I'm just clarifying that there's a difference here, that in R2, I could only specify one basis, whereas in Euclidean space, I can define a basis at, multiple points, at, in fact, infinitely many points. Every single point in this space could, in theory, have a potentially different basis. And so because of these differences, what I'll usually do is I'll usually call Euclidean space, not just a vector space, but a Euclidean displacement vector space. Where really all of this ambiguity, kind of comes from the fact that we can define displacement vectors. Vectors that start, at some arbitrary point and end at another point, instead of vectors that in R2 we would always write down starting at the origin and ending at a different point. Alright, so how does this all relate to polar coordinates, right? Here we go. right? Because the natural question is, given some coordinate system, I'm writing this out for emphasis, is there a natural set of tangent basis vectors to use? Right? And the answer is, of course, yes, absolutely. There's a very natural set of tangent basis vectors to use. What we want to create, right, given any coordinate system, is basis vectors that point in the direction when I increase one of my coordinates, keeping all the others fixed. Sorry if my handwriting isn't the neatest. I'm trying to go fast. Okay, and I'll write down an explicit formula for this in a second, but I just want to point out the ideas first. Right, so before I kind of give you this formula, let me return back to polar coordinates here for a second. Let's just qualitatively figure this out, okay? So here in level 1, we talked about coordinate curves, right? Curves of, fixed r here are these circles, and curves of fixed theta, which are these rays pointing outward. Okay, sure. So, and what I'm saying is that we want to define a natural set of basis vectors that point in the direction when I increase one of the coordinates, keeping all the others fixed. Oh my goodness, look how easy this is. So I'm at some fixed theta here, right? Let's say I'm on this ray. I'm at some fixed theta. Okay, so I increase r, right? Increase one of my coordinates. Let's increase r. What's that going to get me? Okay, that's going to get me a vector that looks like this. And of course, we want to use an orthonormal, right? Normal meaning magnitude of 1 set of basis vectors. So there we go. This is going to look like, I'm going to call this r hat, because I'm just increasing in the radial direction. So this points in the increasing direction of r. Okay, so r hat unit vector. Okay, what about at this same point? Let's go ahead and do the same thing for theta. Okay, so increasing theta with r fixed, oh, that's going to point in this direction, right? If I increase theta some amount, increase theta by some amount, I'm going to work in this direction. We already have this curve that's kind of guiding us. This is going to be theta hat. But look, remember, these are tangent bases. There's nothing that said that these have to look the same at every point. What about this point over here? So first, let's go out in the direction of increasing values of r. So that would be our r hat vector here. And next, let's go in the direction of increasing values of theta with r fixed. Okay, that would be in this direction. Here's the theta hat direction, right? And we can see, again, tangent basis, right? These bases are changing as you move from point to point in my Euclidean space, okay? And I know you guys want a formula to come up with these basis vectors, not just for polar coordinates, but for any coordinate system, and we're so close, okay? Here's the last question that I need to ask you guys. What are the tangent basis vectors in Cartesian coordinates? Okay, what do those look like? Okay, one last time. Let's do this one last time. Well, what are my coordinate curves going to look like? Right? So they're just going to be lines, straight lines, up and down, up and down. So what are my, tangent basis vectors going to look like? Oh, they're going to be constant, right? They're going to look like x hat, y hat, right? But over here, it's also the same thing. Here's y hat, here's x hat, and same thing over here, y hat, x hat. Ooh, that's really a big deal. All right, so what's special about Cartesian coordinates? Well, of course, there was kind of our weak rationale from level 1, which is that they're the common sense coordinates to use. right? But then of course we saw, because we had Pythagorean's theorem, we also knew that distance was very easy to write out in terms of Cartesian coordinates. But now we have this third thing that makes them really special, which is huge. We have constant basis vectors in our space. Or in other words, our basis vectors are totally independent of any, coordinates. So if I take the derivative of x hat with respect to any coordinate, that's always going to give me 0. That's a huge deal, right? And it tells us that really whenever we do any math, in a given coordinate system, we should kind of work with these Cartesian basis vectors as an intermediate kind of deal because of this derivative relationship. I'll show you what I mean. All right, but in general, we should be thinking about 1, our choice of coordinate system, and 2, our choice of tangent basis vectors, okay? And we can mix and match. For example, I could use polar coordinates, but write out a vector in terms of Cartesian basis vectors, okay? So, but in general, right, ideally, we want our coordinate system and our basis vectors to match, right? That would be the ideal. So anyways, let me show exactly what I mean with all of this. So now I'm going to put the definition down. So now I'm going to give you guys a formula. Right, so given a coordinate system gamma comprised of, coordinates gamma 1, gamma 2, to gamma n, right, for Euclidean space, you're only going to have 3, up to 3 dimensions, right, and we can come up with our polar unit vectors gamma sub I hat here, right, by simply taking the derivative of one of our vectors, make it start at the origin, just for your sake, okay, for sanity's sake, take that derivative with respect to the ith coordinate, gamma sub I, and then just divide through by the magnitude of that derivative, right? In order to normalize it, in order to give your ith unit vector some, magnitude of 1. Okay, but let's go ahead and just use the formula in polar coordinates. So in polar coordinates, right? Gamma is we're going to have some radial distance r, and theta. Those are our coordinates. And of course, right, let's go ahead and draw out. So let me go ahead and draw in a vector, right? Call this r. And of course, this connects the trivial point, the origin, to another point, which is at some radius r and some angle theta, right? Where our angle theta is right here. With the x-axis, right? And of course we know already graphically, right, just from inspection that we did before, that our r hat vector is going to point like this, and our theta hat vector is going to point like this. So my point being is that, what is this position vector r going to look like in terms of these polar basis vectors? It's just going to be the magnitude r in the r hat direction, right? There's no theta dependence, okay? But I just said, right, when we're doing math, it's very, very good, right? Because if let's say I just plug this guy in here, right, for r, we're gonna run into problems very fast because I have no idea what dr hat with respect to some ith coordinate is. That's no good. We can't just plug that formula in, okay? So, what we should do instead is we always write this out in terms of Cartesian basis vectors, okay? So now I just go ahead and define, here's x hat, here's y hat, okay? And so now what is r going to be equal to? R is going to be equal to, well, break this guy up. What's this component here? This is r cos theta. This is r sine theta. R is going to be equal to r cos theta in the x hat direction plus r sine theta in the y hat direction. Go ahead and rationalize out this this 1, 2 here. What are we doing? We're writing this vector out in terms of 1, polar coordinates, right, r and theta, but 2 in terms of Cartesian basis vectors. So you see the mix and match that's going on here, right? But we've very strategically chosen to use Cartesian basis vectors for, using this formula here. So let's go ahead and figure out what's r hat going to be. So r hat equals d of r cos theta x hat plus r sine theta y hat with respect to, right, our r, right? We're looking for r hat. We need to take the derivative with respect to r. And of course, we need to normalize this, which you'll see, it's already normalized. In fact, if you just take this derivative and we're going to get out, this is super easy. I'm going to write this out very explicitly just to make my point clear though. So in theory, we would have like four terms here, right? So first, take the derivative with respect to r of this guy. That's going to give us cos theta x hat, right? But then we'd also, right, have to chain rule this, okay? And so we'd have to consider, right, we have r cos theta, but then dx hat with respect to r, right? And now let's do this term here. So derivative with respect to r of this guy is going to give us sine theta y hat. But then again, we have to chain rule here, and we would get r sine theta dy hat dr. But we already said that our Cartesian basis vectors are totally independent of coordinates. So this guy's going to go to 0, and this guy's going to go to 0. Don't take that fact for granted, right? That's a big deal that we can set those guys equal to 0, because in fact it's only true in Cartesian coordinates. It's not true for really any other coordinate system in Euclidean space, right? So Cartesian vectors are very, very special. But anyway, so now we have r hat is equal to cos theta x hat plus sine theta y hat. And now we have a very natural kind of formulation here for our r hat unit vector. Let's go ahead and wrap up this video by doing the exact same thing in determining theta hat. So theta hat is going to be equal to d of r cos theta x hat plus r sine theta y hat with respect to theta over, in theory, we have to take the magnitude of this. And in this case, it's actually going to matter. Right? And go ahead, what's this going to equal? Derivatives are nice and easy now, so we have minus r sine theta x hat plus, right, r cos theta y hat. And it turns out if you take this derivative here and find the magnitude of it, it's just going to be r. So these guys are going to cancel here, and we're going to be left with theta hat is equal to minus sine theta x hat plus cos theta y hat, right? And there we go. We now have defined our unique tangent basis vectors in terms of coordinates, right? And Cartesian basis vectors, which we know very explicitly how to use those, right? So great. But yeah, so I'm going to go ahead and wrap up level 2 here, right? This is kind of the key kind of formula that we really want to use and think about in determining our tangent basis vectors. But of course, hopefully we learned a lot along the way about what that actually means, right? About what is the significance of these tangent basis vectors. And in fact, hopefully we even appreciated, just thinking a little bit about Euclidean space. But if you enjoyed this video, if you found it helpful, consider subscribing to the channel and let me know in the comments. I love to hear about people getting on board. But other than that, thank you so much for watching.